So talking about innovation, it's a great segue. It was already mentioned, Greg Sorensen, who's President and Chief Executive Officer of Siemens Healthcare North America. So Greg, well known to a lot of you, but Greg had a great career previously at MGH, where he led one of the best programs in the nation, in the world, pushing the aspect of imaging, especially brain imaging, magnetic resonance imaging, biomarkers research, etc. So his impact in Boston and beyond is always very well. However, for us, his impact was also very strong. And he's a special guest, not because only of Siemens, but really Greg has been instrumental in guiding us in terms of what the Institute should do and should look like. Early on, we engaged with Greg as a consultant to help us do this. It just happened that our roads kept crossing and crossing again, where we selected Siemens Healthcare as a partner in research, both in our institute as well as in the Department of Radiology. And we're really very pleased to have that relationship. Innovation needs tools, as Dr. Charney mentioned, and I think we're in a very good setting with Siemens to do this. So I wanted Greg, in a sense, again, to thank him for our relationship and looking forward to continuing this. And maybe you can tell us a little bit, Greg, about your feeling here.
Thanks very much, Zahi. It's a real pleasure to be here with you this morning amongst so many friends. Most of you don't know that our initial speaker, David Van Essen, was actually my undergraduate advisor back in the early 1980s. So I really feel very comfortable being here. And as Zahi said, I've been thrilled to be here with Mount Sinai for so many years and watching the development of this fantastic initiative. In my new role, I have a lot of new things that I do, and I thought I'd tell you one quick story just to kind of begin my comments. I spend a lot of time in Washington, D.C. now because of healthcare reform, and last year I was able to attend the White House Correspondents' Dinner and see I think it was Jimmy Fallon or in the President Obama talk. And of course, when you go to the Correspondents' Dinner, it's kind of nerd prom. It's all these various people from education, from the entertainment industry, finance, and government, and it's just a funny mix of people. I felt very much out of place there. But the real event, of course, isn't the dinner, it's the parties before and after. And I was fortunate to go to David Bradley's home, the owner of the Atlantic Monthly, and he told an interesting story that I want to relate to you. It's about a guy named Bob Bennett. Bob Bennett was the lawyer that defended President Clinton during the Lewinsky episode. And after that had wound down, he received a call one evening inviting him to come to dinner at the White House, he and his wife. And so he made arrangements and it came, and when he got to the front gate, Secret Service Marines, the Marines and the Secret Service there, they said, "Oh, you're actually having dinner with the president and his wife in the private residence. So you can just drive your car right into the private residence, not the main part of the White House, but actually where they live." So he drove his car up there, and there were, again, more Marines there when he got out. And they said, "Yeah, this is the right place," checked him in, et cetera. And just as he was going through the door into the residence, one of the Marines stopped him and said, "Mr. Bennett?" He said, "Yes." He said, "Could I ask you a question?" He said, "Sure." He said, "By any chance, would you be from New York City?" And he said, "Well, yes, I am. Why do you ask?" And he said, "Well," the Marine said, "Well, we've noticed that only people from New York City lock their car doors when they park in front of the White House." And I love that story because it highlights the uniqueness of New York. There you are, you've got the Secret Service and the Marines, you're inside the perimeter, and you got to lock your car door. It's just a little bit of, there's a little je ne sais quoi about Manhattan. But I like that because you guys are special here. It's a special place with a special environment, and we at Siemens are just thrilled to be your partners in discovery. The ideas that you're going to come up with, the tools that you're using of ours and developing with us are really critical. When I was a a medical resident, one of the wise guy techs, had put a little sticker on one of the ultrasound machines that was another famous New Yorker saying. It said, "You can see a lot just by looking," Yogi Berraism. And that has stuck with me. You can see a lot just by looking, and we're working with you, and we're excited that you're using our tools to look. And as Dr. Charney said, it's what to look for, what can we see. This is the era where we need to see more than we've ever seen before in order to advance human health and reduce morbidity and mortality. We're really, really enthused that TMII is taking the direction that it is and is going to be able to advance human health really through a rational understanding process. So much of medicine has in the past been serendipitous. And of course, there's always going to continue to be an important role for serendipity and accidental discovery. But some of the best advances, and I think today we'll see evidence of this in many of the talks, have come through a careful, systematic, rational, thoughtful, deliberative process. And that means checking what you're doing as you go along. It means being able to see. And so we're really grateful to have the opportunity to partner with you. The last thing I would say is I think we as a company, healthcare, in Siemens Healthcare, are really in the diagnostics business. We're the largest United States vendor of blood tests. We make a lot of blood tests, and so a lot of the molecules you discover in your molecular imaging approaches, we hope to partner with you to commercialize those as well as the imaging devices. But as I've thought more about diagnosis, I've been increasingly impressed in how it needs more attention and more incentives to get an accurate diagnosis if we're really going to reduce healthcare costs and become more efficient, which is, of course, a critical driver for our country. Frankly, if you just look at the Medicare spending projections, we as a society will go bankrupt if we don't solve that problem. And you can see that it's impacted our ability to fund our research budgets because we haven't yet been able to solve that problem. And so it has real day-to-day impact on your lives. And so it's finding ways to bend that cost curve in an intelligent, helpful way are critical. And I'm increasingly convinced that diagnosis plays a big role in that. It's fascinating to me that that this is getting more recognition. You may remember that just a couple of months ago in BMJ there was an interesting article that analyzed medical errors. And this article pointed out by systematically analyzing medical errors that the category of medical errors that is the most common, the most costly, and the most deadly are diagnostic errors, errors of diagnosis. And again, I come back to this idea that you can see a lot just by looking. If you get the right diagnosis early on, you save dollars, and you develop and use the right therapies. And so this link between optimal outcomes, the right therapy, and the initial starting diagnosis, that's all one seamless chain. And it's very impressive that you've brought all that together here in this environment. So I'm just, again, like to thank all of you for the invitation and for the opportunity to work with you. We're looking forward to a long and very productive relationship together. My own personal relationship with Siemens started in late 90s and is still, obviously, still very productive for me personally, but also at MGH and other places. We are a long-term partner with groups like yours, and you are very special to us. So we're really grateful for this opportunity, and thanks very much for your attention.
Greg, thank you very much. Just to let you know, we've locked actually your luggage to make sure nobody takes it out here. So, okay, so we're doing great. So actually, we're ahead of schedule, which is excellent. And I'm gonna give the baton to Gordon Chu. Gordon is our new recruit for the Imaging Institute. Gordon comes from actually this background of Washington University, St. Louis, not surprisingly, as well as Minnesota, where he worked also on the Human Connectome project and had a relationship with our next speaker. And Gordon's research has added tremendously already to our Imaging Institute with a new innovation in brain imaging and techniques for higher and precision medicine. So we're very proud of him and happy to have him on board.
It's my great pleasure to introduce our first keynote speaker, Dr. Van Essen. Dr. Van Essen is the alumni Edison professor and the past chair of the Anatomy and Neurobiology Department at Washington University in St. Louis. He is well known for his studies of cerebral cortex. Dr. Van Essen's physiological and anatomical study of macaque visual cortex is still considered a classic in the field after a couple of decades. He has pioneered the use of surface-based atlas for visualizing and analyzing cortical structure, function, development, and connectivities, and for making comparisons across studies and across species. His studies of human cerebral cortex provide insights regarding normal variability, abnormality in various diseases, and the patterns of cortical development. He has served as editor-in-chief of the Journal of Neuroscience, a founding chair of the Organization of Human Brain Mapping, and the president of the Society of Neuroscience. He is a fellow of American Association for the Advancement of Science and has received Raven Lifetime Achievement Award from the St. Louis Academy of Science. And he also received a very prestigious Quick Cortical Discovery Award from the Cahoon Club. Recently, along with Camille Ugabil from University of Minnesota, he is the principal investigator of the Human Connectome Project, a $30 million NIH grant to map the brain circuitry in a large population of healthy adults using cutting-edge neuroimaging technologies. I have the fortune to personally observe the great leadership provided by Dr. Van Essen in the Human Connectome Project, not only at the high level, but also in everyday operation to keep the ship on course and on schedule. So David, it's a great pleasure to have you here. Please tell us the latest about the Human Connectome Project.
Thank you, Gordon, for that kind introduction. It's great to be here for this exciting day of events, and it's great to see old undergraduate advisees. Greg, I hadn't seen him for quite a while, and I'm really delighted to have the opportunity to talk to you about the Human Connectome Project. So without further ado, let me say a few words about the brain. I know this is a diverse audience intellectually, and not every one of you eat, breathe, and think about the human brain in the ways that I'm now obsessed by. So let's take a look at some of the basic numbers. So your brain has about 1.5 kilograms of squishy tissue. It's got close to 100 billion neurons. It is dominated by the cerebral cortex, and that's in fact what I'll talk about today. That's 80% of your brain mass, but it's actually only a small minority of your total neuronal count, about 20%. The tissue is dominated by the synaptic connections, literally hundreds of trillions of synapses, and it's wired by literally 100,000 miles or so of connections going through the white matter. There are other critically important parts of the brain. The cerebellum is pint-sized in comparison to the cerebral cortex, but it actually has about 80% of the total neuronal count. And then you're kept alive and well and breathing and heart beating and all good things like that by the rest of the brain, the subcortical structures that are less than 10% of brain mass. And amazingly, they do their wonderful things with less than 1% of your total neuronal count. So with that in mind, the challenge that we're going to grapple with today is how do we untangle the incredible complexity of the wiring of the brain, schematized here in an article by Tom Insel some years ago, and this is a wildly oversimplified version of the brain connections we're going to talk about. So we'll talk about it in the sense of the human connectome. That's one of the latest in the omics. Everyone's familiar with the genome and the proteome and efforts to systematically and comprehensively analyze the infrastructure that gives rise to our genome and our protein contents of our bodies. The idea of omes are comprehensive maps of something, and the connectome is a comprehensive map of neuronal connections, but it really must be forcibly put under quotes because the comprehensiveness really comes at multiple scales. I will talk today about the human macroconnectome. That's the effort to map long-distance connections from one little patch of gray matter to another through the pathways going through the white matter and down to the resolution that is afforded by current imaging methodology, which is voxels or volume elements that are 1 to 2 millimeters on a side. There is a really exciting other world of connectomes that we call, or at least I like to call, the microconnectome. It's the effort to analyze in exquisite detail the location and organization of every neuron, glial cell, axon, dendrite, and synapse in a patch of brain tissue that currently aspires to reach even just a cubic millimeter. That's still aspirational. So there's a vast gulf between the spatial scales by these two approaches, and there's even another world that many of us call the mesoconnectome, which uses other technologies to infer local and long-distance connections. So there's an exciting progress on multiple fronts, but also some great challenges to bridge across these arenas. But to come back to today's focus, it will be on the macroconnectome. And the way I'm going to approach this is to first spend a few minutes giving you some background, some oriented in my roots in studying the monkey cerebral cortex and visual cortex, and then a little bit about the basics of human cortical organization and its variability. Then the main agenda will be to give you an overview of where we are and where we're heading with regard to this exciting human connectome project. So here's the human brain, here's the pint-sized monkey brain from a physical representation, and now in the lower panels a surface-based representation. And one of the things that's obvious at first glance is that the monkey brain, macaque's brain, is much smaller. It's about 10% of the size and surface area of the cerebral cortex. It's a cookie-sized sheet of tissue instead of the pizza-sized sheet of tissue you have inside your skull. Our brains and our cerebral cortex is far more convoluted at a glance, and as you'll see in detail, it's considerably more variable, but there are profound similarities in the organization and function that makes the macaque monkey the best animal model that we have for understanding our own brain. As I say, I've been working on that for decades now, and 20 plus years ago, Dan Felleman and I published a map of macaque cerebral cortex where we pointed out that from the literature there was evidence for the existence of dozens of distinct areas identifiable on the basis of their architecture, their connectivity, how they're organized into visual maps, and distinctions in their functions. So that was the way for parcellating the cortex into visual areas occupying about half of the macaque cerebral cortex, and then dozens of many other areas as well. Another thing we look closely at is drawing from the literature evidence for the richness of connectivity, and we and others were surprised when the tally from looking at the literature provided evidence for literally several hundred pathways interlinking these dozens of visual areas into what we portrayed as an anatomical hierarchy from early to intermediate to high levels of visual processing based on just what we could infer from the patterns of the wiring of the cortical circuits. We also took the same data, several hundred pathways, and generated a matrix of connectivity where each row and each column represents a visual area and a plus represents a pathway, say from V4 to MT and so on. And so this was a binary connectivity matrix because the evidence from the literature at that time didn't allow for proper quantification of the richness of connectivity patterns. I'll come back to that in a moment, but that was what we could summarize decades ago about the macaque cortex. There was virtually nothing known at the time about human brain connectivity because MRI was literally just coming on the scene in the early 1990s. And before I get to the impact of human functional imaging, MRI also allowed us in the ensuing decades to generate better maps of the macaque cortex. So using structural MRI, we could generate computerized reconstructions and flattenings of the macaque cortex rather than the manual, literal pencil and tracing paper maps that Dan Fellman and I had previously made. And onto these macaque atlases, we've been able to represent more accurate parcellations of the macaque cerebral cortex. However, remarkably, that's still a work in progress. In 2013, we do not have a consensus parcellation scheme despite the intensive efforts to identify the distinct areas, but we do have significant progress. And what I'm showing you here is a summary map that provides one current estimate for the existence of at least 130 distinct cortical areas in this mosaic across the macaque cerebral cortex. Importantly, these are not just cookie cutter type representations of different areas. There's literally a range of more than 100-fold from the largest area, V1, which is more than 10% of the cerebral cortex, to these tiny little areas that are nonetheless anatomically and functionally distinct in orbital frontal and other cortical regions. So that's what we have as not a ground truth, but as a progress report that will inform our way of thinking about the human cerebral cortex. Another important advance has come from, finally, a good look at the quantification of macaque cortical connectivity. And this comes from an emerging set of papers from Henry Kennedy's lab, Markov et al. And one example of that is here. So this is the strength of connections from one particular area, V4 in black, and the pattern of connectivity has now been carefully analyzed using retrograde tracers and quantification of every single labeled cell. And what one sees is a spatial pattern that shows more connections that had been previously realized, dozens of connections, on average of 50 inputs and outputs per cortical area. And also in the quantification realm, a basic principle of cortical connectivity, which is expressed as a log normal profile. And the fundamental concept has one component, which is the total range of connection strengths, is literally 5 orders of magnitude, from the strongest pathways, which are massive, to the weakest pathways that are just a handful of cells but may nonetheless be very significant. The majority of connections are in this intermediate range from moderate to rather weak, and this is true for every single area of the 29 injected areas in this study from the Markov et al. Domain. And we can take this connectivity matrix and give you a progress report. It's not completely comprehensive, but it's the most extensive quantification available to date. And from the 29 injected areas of a 91 area parcellation that Markov et al. Used, we have evidence for over 1,600 pathways. And if you extrapolate to, if at some future date we have full characterization, we're dealing with on the order of 10 to the 4th cortical connections in the macaque monkey, and presumably even more in the human cortex. So this is the idea, the progress towards a ground truth that we have from animal models, that we're going to be looking for connectivity matrices of this richness and this range of connection strengths. So with that in mind, now we say, where are we in understanding the human brain and the human cerebral cortex? So I'll start, as I alluded to, with some additional background information. And the first thing is to get our feet wet in terms of the complexity of the cortical convolutions. So here is a high-resolution MRI. Typically, structural MRIs are acquired at a 1 millimeter voxel size, but for the Connectome project, we wanted to get the best possible anatomical resolution, and so we use 0.7 millimeter T1 weighted, as you see here, and also T2 weighted images. And if we take a stroll through the front to the back through a portion of the brain, you can see the complexity of the cortical convolutions, but you can also see these surface contours, the peel surface in blue and the white matter, gray matter interface in green, and you can see that the free surfer segmentation algorithm, customized to give it better quality, does really excellent job in capturing the shape of these convolutions in each individual. That allows us to generate surface reconstructions of the type that you see on the right. So we have a three-dimensional model of this individual's cerebral cortex, and you can see the ridges and grooves, the gyri and sulci, and we can also manipulate the shape of the cortex, so we can inflate it to a smooth surface, but we can preserve the original shape features by what we call a map of sulcal depth. So the darker it is here, the deeper it was in the original three-dimensional representation. And this, as you'll see, is one valuable way of not just capturing, but being able to analyze cortical shape features. Whoops, there we go. So that was one individual subject. I alluded to this issue of the variability of the cortical folding patterns, and that's illustrated by this upper left panel here. So you see the right hemisphere lateral view for 4 individual subjects. And you can see that they don't look the same, but they're kind of like fingerprints. They differ from one individual to another, but the differences are so complex that it's hard to get a good handle on that. And so we can take the same surfaces and inflate them and look at these sulcal depth maps, and now you have, instead of a fingerprint, kind of a cortical brain print. And I can ask you to compare the shape features of these individuals, and that's particularly intriguing because these are 2 pairs of identical twins. So these individuals, 2 of them, each pair has the same genetic instructions, but very different outcomes in terms of the folding patterns. And in fact, I challenge you to assess on the fly who is the twin of case subject W based on the cortical folding patterns. And it's really hard to do. It is possible. A computer can do it well, but the human eye, including mine when we had a competition on this, did strikingly poorly because the variability is so striking. So I can tell you, to cut to the chase, there's a pair of twins, there's a pair of twins, and then look at the differences in the folding patterns revealed by these sulcal depth maps. So this will come back into play when we talk about the Human Connectome project, where we have intentionally targeted twins and their siblings, as we'll get to in a few moments. But at this stage, we can say we know that the convolutions are highly variable. There is a quantifiable degree of heritability, but it's not as much as you might have guessed. Also, the cortical areas that I talked about in the monkey and we'll get to in the human, I'll just tell you that the locations of well-defined cortical areas show some consistency, but also a lot of variability in relation to these folding patterns. So these are some of the intriguing issues, but also challenges that we have to grapple with. And that brings me to a short but important segue about the question of why and how does the cortex fold, and how do we make sense of that? And that's something I've been interested in for many years, and in fact 16 years ago published a hypothesis on the underpinnings, mechanistic underpinnings of cortical folding. The starting point is to appreciate that when the cortex folds is in the late gestational period, the last trimester of normal development. So at the beginning of the 3rd trimester, the cortex in a healthy unborn infant completely lissencephalic, just a few deep grooves like the Sylvian fissure, and then over the ensuing weeks in utero, unless the child is born prematurely, then the cortex starts folding wildly, and by term equivalent or term birth, most of the convolutions are actually present, even though the cortex is only a third its final size. The question of how it folds is schematized here by a hypothesis that it's the wiring within the white matter that drives cortical folding. So we know that as the cortex folds, the white matter is expanding massively in extent, and the hypothesis that I've posited is that at these long distance connections, for example, think of this little part on the right as area V1, we know that it's massively connected with neighboring area V2. If each of those little hundreds of millions of little wires, the axons, was generating just a tiny bit of tension, then if everyone pulls together, that would tend to bring neighboring cortical regions that are strongly connected closer together, forming a gyrus in between, whereas a sulcus would be the outcome of a losing side of the battle, where less strongly connected regions would allow stretching and formation of formation of a sulcus. So that is the speculation. If it's true, it implies that knowing the wiring diagram would predict the folding pattern. It would also allow us to, in one integrated hypothesis, to appreciate that regions where there's consistent folding, such as the central sulcus and the Sylvian fissure, might reflect the consistency of connectivity amongst large size areas like V1 and the somatomotor complex, whereas the highly variable regions, such as lateral, temporal, and parietal and frontal cortex, may reflect the outcome of essentially a balkanized set of little tiny areas that are different in their size and different in their connectivity patterns. All this remains speculation. It's an unproven hypothesis. There are other alternatives, but it's an attractive framework for thinking about a rational appreciation of folding and how to think about it in relation to the wiring diagram of the developing and adult humans. Whatever the mechanism, the reality is that we've got to deal with these variabilities in folds, and we have to, if we want to compare across individuals for any of the countless interesting questions, we have to bring information, data into a common spatial framework. That's been appreciated for decades, since the classic stereotaxic atlas for the human brain was promoted by the French anatomist Taylorach. And the advent of MRI-based imaging has allowed progressively in refinement of atlases that bring individual structural MRI scans into a common spatial framework based on volume-based registration. So here is the result of a nonlinear registration from individuals to a target atlas. And you can see that atlas preserves a lot of shape characteristics, but it's also intrinsically fuzzy because it's impossible to use volume-based nonlinear registration to get perfect alignment of these complex cortical folds. So volumetric registration does actually a great job at aligning the subcortical structures, but for the cerebral cortex and the nature of its cortical convolutions, we and a growing percentage of the neuroimaging community are appreciating the utility of surface-based registration to align individuals to an atlas. And for the Connectome project, we've been using the free surfer Bruce Fischel et al. Registration method. So here is a spherical representation of one individual's convoluted cortex, and we take that individual sulcal map and register it to an atlas target, and that's the deformation one gets. And this is the process of deformation shown in a movie. And while it does a really good job overall, it's far from perfect. You can see there are regions where the registration actually rather severely distorts and contorts the cortical folds more so than would be ideal. And I'll come back to that because we can now do better than that, but this has been state of the art until very recently. With that kind of alignment strategy, one can take maps of human cortical areas and bring them into a surface-based atlas framework, analogous to that which I showed you earlier for the macaque, but now drawing on information about well-defined cortical areas in humans that have been identified on the basis of cortical architecture, particularly some very careful quantitatively analyzed data by Katrine Amundsen and Karl Zullis in Germany, and also retinotopically organized areas in visual cortex that have been characterized by fMRI and are brought into this spatial framework. So here's our current progress report for the human cortical organization, which has over 50 distinct and carefully analyzed cortical areas. And that's the good news. The bad news is that 2/3 of the hemisphere has not yet been accurately mapped using these kinds of surface-based methods, and large portions of it have been not mapped at all well by any method, given the challenges that we have faced. So if we extrapolate and say how many cortical areas might there be in human cortex, we don't have a hard number, but we can estimate that there may be 150 to 200 cortical areas relative to the 130 or 40 we had for the macaque. What that suggests is that our cortex has, during recent evolution, gained additional cortical areas, but only to a modest degree. And so the tenfold expansion in total cortical surface area mostly involves an increased size of individual areas, but also likely some additional newly evolved areas. So if we want to make further progress in mapping the human cerebral cortex, we need more tools. Imaging is central to that, and one component that I'll draw your attention to in particular is what we call myelin maps in cerebral cortex. So most of the myelin is in the white matter, of course, but the myelinated axons extend into the gray matter, and an exceptionally talented student of mine, Matt Glasser, came to my lab with the following idea. It was known from anecdotal observations in the literature that a conventional T1 weighted image has, white matter white, gray matter is gray, CSF is dark, and the gray matter is not uniform in its intensity in a T1 images. It's brighter in some patches and darker in others. And the converse is true in T2 weighted images where the white matter is dark, the gray matter is gray, but there are some patches that are brighter in a T2 weighted and darker in a T1 weighted image. And Matt's idea was he noted that those tended to be complementary to one another, so he did the math. That is, he said, why don't we take the ratio of T1 to T2 intensity voxel by voxel and then colorize it to make it not only prettier but more informative, to see that there are regions where that ratio is high, and that turns out to correlate, to give a very beautiful spatial pattern when we map these T1 to 2 myelin estimates onto the cortical surface of an individual. And you can see that there are heavily myelinated regions in red and yellow in the sensory motor strip, which is known, in fact, by classical anatomy to be heavily myelinated. Ditto for the auditory cortex and the visual cortex. And in fact, there's a remarkably good alignment with the pattern of myelination that was known for more than or almost a century to reveal regions that are myelinated relatively early in development, and this classic analysis by Flechsig showed the pattern of early myelination, and also studies by Hopf and others showed that these, the regions that myelinate early remain heavily myelinated, and so we have a qualitative validation of this approach, but most importantly we have an in vivo method for estimating myelin content that can be applied, and you'll see the utility of that as we now finally move to the Human Connectome project itself. And I can tell you the origins, but most importantly the progress that we've been able to make. So this is an initiative that was inspired by a bold concept from the leadership of NIH. They offered $30 million to an effort to chart what we call the macroconnectome and how it varies in healthy adults. And it turned out that NIH was enthusiastic enough, they awarded to two consortia, one led by WashU and Minnesota and Oxford University, and has 10 institutions overall, and Camille Ugerbill from Minnesota and I are the PIs of this effort, and we've pulled together a team of over 100 individuals at these different institutions to work intensively at mapping the human connectome. And then, as I said, there's a parallel effort led by Bruce Rosen and others at MGH and UCLA that, as I'll touch upon later, but I will focus on the efforts of our WUMIN consortium, as we call it. And early on we decided that we should not just draw from a random Streets of St. Louis pool, but we should target twins and their siblings to be able to tackle these questions of the heritability of brain circuits, and also use the genetic linkages to improve the eventual genotyping analyses that we'll be able to do. So we're aiming to study 1,200 healthy adults using cutting-edge imaging. So we worked with Siemens and were able to persuade them to take their latest 3 Tesla Skyra scanner and soup it up with a strengthened gradient insert that came from the 7T line, but it was inserted into the Skyra and gives us greater gradient strength. That you'll see the benefit we get from that. And so all of our subjects will be scanned on this 3T Skyra that's centered at WashU, and 200 of these same subjects will, starting this fall, go up to Minnesota and be scanned at 7T, so we'll get the benefits of what the latest imaging methods at 7T can provide. We're using advanced pulse sequences. Multiband parallel imaging is at the core of it, and I'll come back to that briefly, but that's been central to the higher quality data we've been able to get. And we're doing this for 4 imaging modalities. The structural imaging that I already showed you, the utility of getting higher resolution, higher quality, but also diffusion imaging leading into tractography to estimate anatomical circuits, resting state fMRI, and task fMRI. I'll show you particularly for resting state where we are on that front. And we're using MEG acquired at a MEG facility at St. Louis University, and targeting 100 of these subjects for MEG analysis. We're getting highly detailed, several hours worth of behavioral data from each of these subjects, so we'll have extensive phenotyping to which we can relate brain circuits to individual behavioral characteristics or constellations of behavioral characteristics. We're taking the blood samples from every one of these subjects, and we'll do genotyping in the final year of the project so we can get the highest quality and most affordable, potentially, we hope, whole genome sequencing, but that depends on where that cost curve. And then we're making this data freely available and not just in a giant core dump repository, but in a well-organized informatics platform, and I'll give you some of the feel of that. So we want this to be a resource for discovery science by the community at large, and a baseline for future studies of brain diseases and disorders. NIH made what I think was a good decision to study healthy adults to give us that kind of information base on which future studies could be based. So where are we? We're a little over halfway through the project now, and we spent the first 2 years in an intensive effort to improve everything that we could get our hands on that might be made a little or a lot better. So I've already mentioned the improved customized scanner was one part of it. The pulse sequence improvements are major, and that was a huge part of the overall effort, but it wasn't restrained to that. You'll see some of the improvements in the analysis methods within each modality and the ability to make comparisons across these different imaging modalities and to make it available with a visualization platform that lets us drill down in great detail. If you're interested in some of the fun or gory details, depending on how you look at it, there are 8 papers that have just come out in a special issue of NeuroImage that really drill down into the advances that we've made. Last summer, almost a year ago, we launched what we call Phase 2, which is taking the finalized pulse sequences for each modality at 3T and scanning subjects at high throughput. And we're now over 260 subjects in less than a year. And we've had 2 quarterly releases of these data sets already. It takes months to really clean up and process the data for reasons you'll see. But we're making the data available and working to continually improve the data mining capabilities, and then we're committed to making the data available throughout the remainder of the current decade. So why is the data better? Again, better scanners, but also pulse sequence improvements, and the biggest single type of improvement is from this simultaneous multi-slice or multi-band imaging. The concept has been around for more than a decade. Both the MGH and the Minnesota groups have pioneered the refinements to these methods. Gordon Zhu was absolutely pivotal to the effort to really tune these sequences for the SCIRA scanner. And the basic idea is that rather than acquiring data one slice at a time, one can excite up to, well, you can excite as many slices as you want. We're, for the 7T, pursuing 10 to 12 slices at a time. But what we consolidated on for the 3T fMRI scans is exciting 8 slices at a time, and then using a 32-channel multi-channel coil array to extract this data and unalias and reconstruct the scene of the crime, the slice-by-slice spatial pattern of alignment. So 8-fold slice acceleration for fMRI, 3-fold was what we were able to achieve for diffusion imaging, and this gives you a lot more data of higher quality, greater signal to noise, and the ability to resolve at higher spatial resolution and higher temporal resolution. When we get these data, then we need to process them as well as possible, and you're not meant to read all the fine print here, but I'll just give you the big picture that we, for each modality, including the structural imaging, put a lot of effort into analyzing the data to get as high a quality reading of the signal and remove as much noise and bias and uncertainty as we can. One example of this on the structural side, so I mentioned the free surfer segmentation method. It's a workhorse tool, but conventional free surfer applied to conventional 1 millimeter structural images does about as good as you might be able to hope, but it doesn't do a perfect job. And so here is one individual subject. The green contour, sorry, the red contour shows you what free surfer's conventional output is in a region of the central sulcus that is thin and heavily myelinated. And basically, it cannot and does not do a great job using conventional imaging, but using the higher quality structural images and improvements to the algorithm itself, Matt Glasser and Bruce Fischel and others worked to get the green line, which is a much better estimate of the exact trajectory of the gray-white boundary. And the point of this is this gives us a better estimate of the actual structure, better estimates of myelin content because we're accurately estimating the surface contours. And then we take these data and we bring them onto an atlas surface and use these data sets for the kinds of analyses that I'll now turn to in a moment. But there's one other important methodological part of the story, which essentially has to do with working optimally with the geometry of the brain as it delivers itself. So I've made the point previously that for looking at cerebral cortex, we really need to use surface reconstructions that respect and capture the topology of these complex convolutions. And that requires a geometric tessellation that is not a set of voxels, it's a geometric mesh. And we want to do that separately for the left and right hemispheres because they're topologically separated from one another. But we also want to capture data about connectivity that associates with the subcortical structures, which are not sheet-like structures. The nuclei are blobs of tissue, and we don't want to force them into separate data representations just because that's the way the geometry of the brain is organized. So we spent a considerable time thinking about and then implementing a conceptual and an data format that is rooted in what we call gray ordinates. So a gray ordinate is a surface vertex if we're talking about cerebral cortex, and it's a subcortical voxel if we're talking about the subcortical nuclei or the cerebellum. And we have a new data format, we call it the SIFTY format, by analogy with NIFTY that is standard in the field now for volume data. GIFTY has been standard for surfaces. SIFTY stands for connectivity format, and it combines the two in a way that is compact and efficient. And one of the reasons it's important is that when we look at connectivity, structural or functional connectivity, we have massive data sets because we're estimating the connectivity between each gray ordinate and every other gray ordinate. And if we were to use a conventional volume-based representation, we would have almost 200 gigabytes to store the data for each individual at the spatial resolution we can acquire. And we can get a six-fold reduction by using this more efficient SIFTY format. So I belabor this because it's going to take a change in the mindset for the field to get on board, but there's really good conceptual and practical reasons for going down this road. Where does it get us? Well, it lets us look at brain activity and brain functional connectivity in the following way. So here's the anatomical substrate showing the left and right hemispheres of one individual. Here is one moment in the life of this individual in the scanner, the one frame of the fMRI, the bold signal, which we know is an indirect but very valuable indicator of recent neural activity. Over the past several seconds, whatever the brain activity it has impacts the bold signal, and we're representing it here as fluctuations above and below the mean value to regress out some of the noise components. That's a technical issue that is very important, but I'm just going to cut to the chase and say that we can represent that pattern of brain activity on the cortical surface and in the subcortical structures of this individual. We can also map the data from the cortex back onto the cortical slices. And now we're going to show you a movie in just a moment, and to get your focus, I want to note that there are patches that are high in activity in this initial frame, patches that are low, and if we turn the movie on, you can see the moment-by-moment fluctuations in brain activity that is essentially the cortical symphony that goes on in everybody's skull, whether you're awake and paying attention, I hope that's still true, or if you just tune out and don't actually try to do any task, your brain is still very active. So this is what we call the resting state signal, and you get a flavor of as I say, this symphony of fluctuations. What was initially high may turn cool, what was initially cool may turn hot, and yet it's not random, it's orchestrated in a complex spatial and temporal pattern that informs us about brain circuits. And that's the fundamental idea of resting state functional connectivity, to use this data to advantage to infer what are the local and long distance functional interactions or correlations that may relate to brain circuits. A conventional fMRI scan does this at 3 millimeter spatial resolution for maybe 5 or 10 minutes. For the Connectome project, we have the higher resolution in space, 2 millimeter voxel size, faster time frames, 0.7 seconds per frame, and we acquire 60 minutes worth of data to get as much as we practically can from each individual. And then we take that data and we analyze it, and the fundamental concept of that analysis is a correlation-based strategy. So for gray ordinate number 1, there's a time-varying signal. It's slow, but we have an hour's worth of data. And for gray ordinate number 2, we have a different temporal pattern, and we ask, are they strongly correlated or anti-correlated, having regressed out the mean, or somewhere in between? And we do that pairwise for every set of gray ordinates, and we get a 32K by 32,000 connectivity matrix, or what we also call a functional dense connectome. And that's one corner of that massive 30 gigabyte matrix. We can read that out one row at a time. So if I ask, what is the functional connectivity pattern for location 1, you can see that it is strongly correlated with nearby regions in the parietal lobe of the right hemisphere. It's also strongly correlated with a similar region in the left hemisphere, and correlated with long distance regions up in frontal cortex. So that's a functional connectivity map for a seed gray ordinate or vertex location in parietal cortex. If I choose another one, I can read out a different row and see that there's a totally different spatial pattern. So this is the idea, and I talk about this readout because we can read this information using the Connectome Workbench visualization platform we've built for the Connectome project, and we can read the data at a distance. So rather than asking to ship 30 gigabytes over the internet tediously, we can just read one row at a time and interrogate our distant database and be more efficient about this strategy. So here's one more example of a seed location that's in the left supramarginal gyrus. That happens to be a region that is known from previous task fMRI studies to be a domain that is activated in many different tasks. So its functional characteristics are associated with a variety of tasks. And if we look at the spatial pattern of these task activations, we're seeing part of again, what had been reported as a task activation network in classic studies, and the functional connectivity correlates with that task activation pattern, and we can see that in an individual and in a group average, as you see here, averaged across 25 different subjects. So we get greater signal to noise when we take the group average, but it also gets spatially blurred out because we have not done that great a job in reducing the intersubject variability. And that turns out to be a huge issue, but it's one where we can report progress on improving the intersubject alignment. And one aspect of that is to use as many modalities as we can, and one of those modalities is the myelin maps that I talked about before. Our motivation for that is illustrated here. So this is a seed location back in occipital temporal cortex in a region that's known to be a motion processing complex known as the MT plus region. And if we look at the functional connectivity in this individual, you can see a complex pattern of local and long distance functional connectivity. And if you look at the myelin map of the same individual, you can see that the hotspots of functional connectivity co-localize with hotspots of heavy myelination. So there's a cross-modal validation at the level of individual subjects that suggests if we could use myelin maps and functional connectivity to improve registration, we might get a better job, a better outcome, and we can indeed, and I'll illustrate that in a moment, but I want to illustrate in the next couple of slides why we care about this and also why we have already benefited from the high quality data of the Connectome project. So here's one more example of a seed location. Now this is on the medial aspect of the hemisphere, and if we put a seed location in retrosplenial cortex just above the corpus callosum, you see this pattern of functional connectivity in one individual, and in a group average, again, better signal to noise but spatially blurred. And if we take a seed location that's literally just a few millimeters away, more dorsally, you can see in this posterior cingulate seed a totally different connectivity pattern. So if I just jump between the two, you can see the radical differences in functional connectivity between very nearby brain locations. So that's why we're obsessed with getting the best spatial accuracy that we can and preserving it as we go down the road. Now, coming back to this issue of alignment across subjects, the free surfer method, which is based just on geometric shape characteristics, the folding patterns, actually does a really fine job in regions where there are major sulci that are relatively consistent, such as the central sulcus. So this is a map of architectonic area V1 or area 17 across a population of subjects, and they are well and consistently co-localized by shape-based registration. Whereas out here laterally in this region, the MT complex I mentioned, that's also an architectonic area whose particular label is HOC5, but in a group of individuals, they're just not well aligned by using shape characteristics because the folds are so different. So you don't have the information on which to do that. So the good news is our colleagues in Oxford, part of the HCP consortium, Emmy Robinson and Mark Jenkinson and others, have developed a new algorithm, what we call multimodal surface matching, that can use as many modalities as you have information available. And we've been able, with Matt Glasser in my lab, to take the connectivity data and use not just the shape patterns, but also the myelin maps and the functional connectivity maps, and to improve the quality of intersubject registration. And just to illustrate the proof of concept, in the upper panel you see the alignment achieved by the conventional shape-based free surfer method of myelin maps for a group average and functional connectivity for a seed in area MT. And you can see the quality of alignment is considerably sharper, particularly up here in the parietal and frontal lobe areas, both for the myelin maps and for the functional connectivity. And we're still, pounding hard on this, but we're quite confident that this approach is really giving us better alignment across subject, which is going to be critical for the kinds of analyses that we want to be doing. And I'll illustrate some of these analyses in the next few slides. So one strategy for analyzing functional connectivity and networks in a group of subjects is to use independent components analysis, an effort that's used by a number of groups, but Steve Smith and the Oxford group have really helped lead the way in developing the analysis methods. So if one identifies resting state networks based on regions that have a commonality to their functional their time signature, then you can see here is a conventional slice-based view of resting state network number 1. So all of these voxels here have similarities in their time course, and they are different from resting state networks 2 through 22 in this particular analysis. We can take these same data and map them onto my preferred surface-based representation. So each one of these then shows a resting state network that tends to be spatially clustered, but within one network you can have local and long distance similarities in time course that define each network. And then we can take this kind of strategy and say for, in this case, the 22 networks from a group average of 20 of our initial bolus of HCP subjects, what do we learn about the functional connectivity between resting state network 1 versus 2 and all of those pairwise comparisons. So it's the same idea as I've previously illustrated for the 30,000 by 30,000 network, but now we can condense this into a more compact and compressed or parcellated representation, and that's what you see here. So this is a functional connectivity matrix, more like the one that I showed you for the macaque monkey, where we group regions into well-defined parcels. Now the parcels are defined by the functional connectivity itself, and what you see here on the lower left is the full correlation matrix, the degree of correlation between each resting state network and all others. And some are strongly correlated and some others are not. Now, we can take those functional correlations and regress out all of the common features and generate what we call a partial correlation matrix between each resting state network and all others. And it's a sparser matrix because it's regressed out all the common inputs. And each of these measures has its own utility. Neither one of them is telling us actual anatomical ground truth, but it's giving an estimate of what functional connectivity informs us about brain circuits. And we believe that the partial correlations is probably going to be more informative, but it's really part of the philosophy of our Connectome project is not to force answers down people's throats, but to provide multiple representations and let the field help analyze and interpret these kinds of data sets. But the quality of the data lets us not drill deeper, and so hot off the press, here is a more rich, finer-grained connectivity matrix. It's the same concept I showed you before, but now we've analyzed 66 subjects, and the data quality allow for a finer-grained parcellation into 82 components, and you have the same concept but a richer representation at the level of a group average of the functional connectivity matrix of this population. But for the Connectome project, as I've made clear from the outset, one of our objectives is to analyze not just group averages, but drill down into the level of individual subjects. And so we can take the functional connectivity matrix of each subject using this independent component analysis based parcellation, and as Steve Smith has done here, generate a partial correlation matrix at the level of individual subjects, and then do that for all of the 66 subjects that are in this data set, and make comparisons across individuals. And one of the first things we were keen to do was to compare individual twin pairs and see, is their functional connectivity matrix more correlated than you'd expect by chance? And the answer is basically yes. So this is a functional connectivity analysis at the level of individual subjects, where we've grouped these into individual twin pairs. And basically, the strong correlations along this diagonal is telling us that the heritability is indeed, of functional connectivity, is indeed much higher for individual monozygotic twins than for unrelated or dizygotic twins. And when we do just a cross correlation, you can see that the correlation of the functional connectivity matrix for monozygotic twins is much higher than for dizygotic, and even higher, or dizygotic in green, and much higher than for non-related. So this is just the beginning of our ability to show that there is heritability of brain circuits as well as other characteristics. And that will be an exciting work in progress that we and others can explore. One last important point about functional connectivity, because I've talked a lot about the organization of cortex into anatomically defined parcels, it's an important and neurobiologically robust feature of cortical organization that the anatomical wiring of cortical areas is not totally uniform across all regions. And to illustrate more specifically what I mean, on the left here is an architectonic parcellation based on postmortem anatomy, but also confirmed by the myelin maps that I've shown you previously, of the areas of the somatosensory and motor strip. A set of strip-like regions, each one has a map of the cortex on it, of the body surface. The functional connectivity revealed by this ICA-based analysis shows that the functional connectivity of this region of the face representation of somatosensory and motor cortex is very different than the arm or body representation. So, in other words, the similarities in connectivity across cortical areas is greater than the connectivity along the length of this strip. And so connectivity analyses, both from in vivo imaging, but similar results have been found in tracer studies in macaque, tell us that the parcellation we define by architectonic analyses and the parcellations we define by similarities in connectivity are actually not the same. And that's not an artifact of the method, it's a reflection of brain circuits. So I want to move quickly along. We're running we're no longer ahead of schedule, but I've got a long story, as you can see. I just want to make a quick point that these methods, functional connectivity and all of these imaging methods, as exciting and powerful as they are, they're also complex and indirect measures of the anatomical circuits that we want to study. And we should always be mindful of that, be critical of the analyses that you carry out, and don't overinterpret the data. And similar issues arise when we look at diffusion imaging, where we've got these opportunity to explore the wiring within the white matter itself. So these are the cables that you can see, the spaghetti-like patterns of connectivity within a physically dissected brain. But each of these little patches contains hundreds of thousands of axons, and we know from dissection, as well as just the inferences from monkey connectivity, that the cortex has a whole lot of cross traffic in the underlying white matter. And so the challenge of diffusion imaging is not just to estimate the dominant orientation of fiber bundles in each voxel, but to infer where there's evidence for crosstalk of these cables going from one location to another. The good news is that the improvements that we've achieved with the Connectome project through a stronger gradient strength and improved pulse sequences allow us to analyze diffusion imaging at much higher spatial resolution than the standard 2 millimeter voxel size. So we've gotten at 3T down to 1¼ millimeter voxel size, and the quality of the diffusion imaging data that we get is much better just at a glance. So on the left are fiber orientation estimates and fractional anisotropy estimates from a conventional 2 millimeter protocol, and with the HCP 1¼ protocol, you can see it's higher quality at this level, and that quality extends to the level of estimating long distance trajectories using probabilistic tractography. So using a conventional image data set and a seed and motor cortex, you can see some long distance pathways, but you see more of them, and we believe more accurate representations using the higher quality Connectome data. We can extend that all the way to looking not just at connections down to deep subcortical structures, but when we want to look at cortical connections, we can take a seed location, say in the inferior frontal gyrus, and look at the trajectories of fiber bundles using the estimates from the FSL method of inferring fiber orientation, multiple fiber bundles in each voxel, and we can take the subset of trajectories that are associated with any given seed location and look at the probabilistic distribution not just in one slice but in 3 dimensions, and we can take this volumetric view and as it were rock the boat and give you a sense of the richness of the 3-dimensional trajectories that we can view from any chosen seed location at the cortical gray-white matter interface. And we can do that not just to infer the trajectories through the white matter, we can connect all the way to cortex gray matter to gray matter connections. So this is the structural or tractography-based connectivity of a seed location, in this case in the inferior temporal gyrus, and you can see local and long distance connections in parietal and frontal cortex. And now, because we have multiple modalities for each subject, we can compare this with the functional connectivity in the same individual, but now using resting state fMRI. And you can see that there are strong similarities in the functional connectivity, but also substantial differences. There are false positives and false negatives. And those discrepancies, some of them may have neurobiological origins because the functional connectivity can reflect indirect as well as direct connections, but some of them reflect biases in one or both of these methods. And to illustrate one of those biases that we need to be mindful of, first conceptually, there's a gyral bias that we can expect to encounter just from appreciating the geometry of how the white matter feeds into what we call a gyral blade. So here is a little blade of a gyrus with white matter underlying it, and conceptually we imagine that the bundles of axons running up into a gyrus are peeling off to get inputs coming to or emanating from the cortex on either bank of a sulcus, but the diffusion imaging, because it's much coarser than individual fibers, is going to be dominated by the, in this case, vertical orientation that points towards the crown of a gyrus. And that, in fact, is seen in diffusion imaging, that if you just count the number of streamlines that are connecting to different regions of the cortex, the strongest connections are on the crowns of gyri. In humans seen in vivo, and actually even in high-resolution monkey post-mortem analyses. And And yet, from the kinds of retrograde tracer anatomy I touched upon early in the talk, we know that there are as many, more or less as many connections emanating from the banks and depths of sulci as there are from the crowns of gyri. So this apparent bias is not a reflection of neurobiological reality, it's a reflection of the features that the diffusion imaging shows with the limits of current spatial resolution. And we have post-mortem analyses that we've been doing with staining for myelinated axons in the white matter to actually look microscopically at the trajectories of axons and fiber bundles. And we do see subjective confirmation of the kind of peeling off pattern that I schematized before, and you can actually see that as axons peel off. And so all of this is a pointed reminder that we, even with the exciting advances in diffusion imaging, we are not at the endpoint that we want. We need better data. We may be able to get better data, for example, from the even higher gradient strength provided from the scanner, the connectome scanner at MGH. We need to understand the anatomical realities that postmortem analyses can provide. We need better algorithms to analyze the data and estimate where fibers are just peeling off, even though we may not be able to see that in each voxel. We may need to model it to reflect anatomical ground truth. And we need, in the meantime, to make sure we don't overinterpret the connectivity data that we are able to extract and infer. In the last few minutes, I'm just going to give you a whiz-by of the other modalities. I've concentrated on resting state because that's where we're farthest along in understanding interpreting. But we have an hour's worth of task fMRI from each of our individuals and 7 different tasks. And we can analyze and represent, for example, the activation associated with viewing places versus other objects, or the activations associated with viewing social interactions versus random movements of these little triangular icons. We can compare task activation to resting state functional ICA components and see that they are amazingly similar. That's another flavor of cross-modal interaction. We're getting MEG data, just started acquiring it from our optimized MEG design, and we're getting resting state as well as task evoked MEG. That'll be another exciting modality because it gives us millisecond time resolution, even though it's more centimeter scale on the spatial resolution. And then, as I alluded to before, we have extensive behavioral data. I'll not spend time other than just give you a flavor of behavioral assessments across the spectrum from cognition, emotion, motor and sensory, personality features, and extensive demographic data that we acquire and will be making available. As I say, we've made the data available already. You can have the unprocessed data if you want, but we strongly encourage investigators to capitalize on what we call the minimally preprocessed data that we have for each of the subjects. We will be releasing more advanced level analyses, but that's still a work in progress. All of the imaging data and most of the behavioral data are open access. You do have to agree to online data use terms. If you want information about family structure, that gets into a realm where it's more of an important issue to preserve subject confidentiality, and so we have restricted access data use terms. But you can get to these data by going to our ConnectomeDB website, and you can download data for individual subjects, or you can go drilling into the database and filter by different phenotypic characteristics. And then, as I said, there's publications that give you great detail about the information that's contributed to this project. And so to wrap up, we're still really early in a grand challenge for our century, if not longer, of understanding human brain circuits. The Human Connectome Project will give us a great deal of information and insights about connectivity and how it varies across healthy adults. We'll see really exciting discoveries and insights, I have no doubt, but we're not going to get a complete connectome, at least in my lifetime, that really spans the realm from macro to microscopic. So we need to be very optimistic, but keep a critical eye on the data and manage our expectations, and be optimistic, however, that this will inform future studies that will improve diagnosis and treatment of development and aging and myriad diseases. So I can't say enough about working with a fabulous group of investigators. Camille Uverbill has been a wonderful colleague to work with, and I've mentioned many people, but Matt Glasser, my graduate student, has contributed with particular importance to many of the things I've had the opportunity to tell you about. So thank you for your attention.
We can take some questions here. We have microphones because this is being recorded. So if you have questions, we'll bring a microphone to you. Yeah, Yasmin. Can we have a microphone, please? Or do you have it? No.
Can you hear me?
You have the microphone. Oh, they're here. Okay. Oh, here, these two. Okay.
It's really, I don't know, is it on?
It's on,
Yeah, it's really wonderful, and I know it's in the beginning of the connectome, understanding all of the nuances, and then trying to get into the biology. Have you gotten any sense yet as to gender differences?
Steve Smith has started to analyze that, and the short answer is there is sensitivity to gender differences. We have really not begun to probe that in any detail, but I believe it will inform us about that in interesting ways. So that's a we're just at the level of having early probes of that. But again, the community has access to these data, and there are so many possible questions that it's open for business for people to think of what are the most important questions and how best to probe any issues of that type.
So what implications does it have for the classic Brodmann areas and so forth that we've used to define different regions of the brain? Is that gonna be
I think of as a cortical cartography, I often use the analogy with maps of the Earth's surface. You know, the 17th century maps were fairly accurate in some regions and wildly inaccurate in others. And the same is true, you know, Brodmann nailed Area 17, Area 18 was part right and not perfectly so. The somatomotor regions he got right, but in the regions of high variability, he didn't do so well. You know, Area 7 or an Area 5 we now know as a mosaic of many finer areas, but we do not have yet an accurate map. We have the tools for generating those through the connectivity data and the improved inter-subject alignment, but that is very much a work in progress. So in a few years, we'll have a much better story.
Just one follow-up then. With deep brain stimulation, now being a therapeutic option in Parkinson's, dystonia, and now even in some neuropsychiatric conditions, what are the implications of what you're going to find or are finding for where should we be putting these electrodes based on what we're learning about connectivity? And how will that inform?
I hope that it will inform our ability, particularly for depression, and which is a stimulating cortex or subcortical white matter, that we'll have a better understanding of the circuits that are being stimulated and the variability in those regions that are currently, Helen Mayberg and others are just probing without as much information as they would like about the nature of variability in those circuits. For subcortical structures, again, it's been an empirical, this works, and we think we have guesses as to why it might work. If we can understand the actual connectivity better, we may have a strategy for more rational placement of electrodes and for positioning it. Certainly, the Minnesota group, in terms of deep brain stimulation, has already demonstrated the utility of 7T imaging for giving finer spatial resolution. That's another story that I didn't have time to really talk a lot about, but 7T is going to inform us a lot by capitalizing on the higher spatial resolution that it provides.
David, it seems like one of the strengths of your data set has been this the twins, and you show just the beginnings of a sense of what's heritable and not in the connectivity. Can you just touch a little bit more about that? Will that lead to Brodmann-like maps of these are what's common? There isn't really a Brodmann-like map of connections yet, of major connections.
Right. So again, we're just at the cusp of drilling into this, but in this heritability analyses, Steve Smith and Tom Nichols have been able to make initial inferences of which circuits are the most heritable, and we have teasers that we're probing into, but again, it's a moving target, because just as we've gotten this finer grained registration methods, we're going to redo that because it's going to give us a better power for looking at these heritability. But the fundamental question of not just saying there is heritability, but what aspects of brain circuits are contributing to that is actually one of the most exciting things I'm personally interested in exploring.
Very cool.
Do you have a chance to look at stability patterns? So any type of longitudinal follow-ups of any of those subjects, just to look at stability, reliability, but also effect of age and duration and time.
So we were obliged, well, we do not have a full-blown longitudinal analysis planned. We have acquired repeat scans from several dozen participants so that we will be able to look at methodological estimates of stability. That's a different question than longitudinal studies. However, these subjects are in principle amenable to future longitudinal analyses. So there may be projects separately funded that can capitalize on this as a baseline and go back and look at changes in the future.
Thank you, David, for a fantastic talk.